Bonjour tout le monde. Bon matin, bienvenue. J'ai le plaisir de vous présenter James Craig, qui est professeur à l'Université de Waterloo. James est un collaborateur d'assez longue date d'Ouranos. On a commencé à travailler avec lui dans le projet Avec Hydro en, je pense, 2018. Fait que James dirige une chaire en hydrologie, en analyse hydrologique à l'Université de Waterloo. Puis il était à Environnement Canada cette semaine pour parler de l'intégration de Raven dans les schémas de surface, donc Environnement Canada, qui a pris généreusement le temps de venir ici à Ouranos ce matin pour nous parler de ses derniers travaux. James, the floor is yours.
All right, thank you very much. Thank you very much for the invitation to speak here today. Hopefully the audio is all good and the owl is finding where my head is here. So I'm going to be talking a little bit about advances and challenges, mostly challenges more than advances in terms of how we connect climate model forecasts, propagate them through hydrologic models in order to do impact assessment, both in terms of hydrologic impact and downstream beyond hydrology impacts. So I'm going to spend some time summarizing the modeling chain from climate model to hydrology model to downstream models. I'm going to discuss 8 major challenges in propagating climate forecasts through hydrology models. Some of these are challenges that have been well addressed in the past. We have solutions for those challenges. Some of them have been partially addressed with some success and some failure, and some of them are kind of open questions, I'd say, and there's still plenty more challenges, and 8 is an arbitrary number. It's just the number that I came up with as I was putting this talk together. There's probably an additional 12 that we get up to a nice round number, but we're going to discuss 8 here today. And then I'm going to spend a little bit of time at the end discussing how we address uncertainty in those impact predictions from hydrology models, maybe think about how we address uncertainty in both simple means of doing so and more advanced means. All of this is going to be discussed in the context of research efforts at the University of Waterloo, where we work to build better hydrologic models, better methods for hydrologic modeling, hydrologic modeling workflows and data products that are not directly aimed at climate impact assessment, but rather are aimed at a number of different applications, which include climate impact assessment. But as we've gone through and developed these, some of the hooks and tools and methods have been used for this type of application. So I am a model developer, more so than a model user. I do use models, certainly, but so this perspective of this talk is coming from my perspective as somebody who builds models, who actually gets in under the code and tries to make them usable for all these applications. And as I said, because there's so many unsolved climate change analysis problems, I'm going to be focusing again mostly on these unsolved problems more than things that we've done at Waterloo to solve all the problems in the world, which we can't admit to. So let's look at hydrologic simulation models. What do we use these for? Well, they are commonly used in forecasting. So we use models to make short-term and seasonal predictions of floods and or inflows to a reservoir for hydroelectric power generation often. That is going to change as climate changes, but that is not really a concern when we're talking about impacts for short-term forecasting. We use models to improve and assess our scientific understanding of what's happening in watersheds. We use them for hypothesis testing, to confirm or reject conceptual models about how the world works. We use hydrologic models for design. So we take estimates of 100-year precipitation or 50-year, 20-year precipitation of certain intensities. We propagate those through hydrology models in order to determine the magnitude of design floods. That might be peak flows, that might be peak volumes of flows from these frequency-derived storms. We also use them in reliable design. So we would try to use models to assess potential system reliability, and that might be for cascading reservoir systems and how we manage them, how we design them. Lastly, we use hydrologic models for simulation or scenario analysis. We use them to ask, what if we change our forestry practices? What if we change our agricultural policy? What if we change how we allocate water in water scarce regions? And so we say, what if certain things happen? And so we're trying to understand the potential impact of things like forest fires or pine beetles or glacier melt. And it's these two areas of application, design, and scenario analysis, where we're looking at longer time horizons, 20 years, 50 years, where we really have to account for changes in climate. And so the big problem here, of course, as everyone in this room knows, is non-stationarity. So as we have a changing climate, our hydrologic analyses, the ability to make predictions about what the 100-year design storm should be, faces challenges. We have issues that historical data for informing decisions is just not as valuable, because historical data is not reflective of the future. We have issues where frequency characteristics are changing, and they're changing to an unknown degree. So we no longer know what the 1 in a 100-year storm event is. We no longer know what the 7Q10 meteorological drought is. We can no longer then propagate those through our models to figure out what the 100-year flood event is, or the 7Q10 hydrologic drought is. So those are unknown, and they will continue to be unknown. We always have a hard time getting those probabilistic estimates when we already have a hard time with this historically, because we have limited data records. And now we're trying to say something about this in the future where we have 0 data records. We have issues where our extremes may be more extreme. So we need to estimate things like probable maximum precipitation. Again, we have a hard time doing that in fully stationary conditions, and now we're trying to propagate that into the future, high uncertainty. And then we have things where it's not just the meteorology as a boundary condition controlling the hydrology that's a problem. We have the system is responding to climate change, and its response to different forcings of precipitation and temperature is also changing. So melting permafrost is an example of that, where the landscape changes due to melt, its hydrologic response to events that changes, and we need to be able to handle that as well. So that's another form of non-stationarity that's happening on the land surface rather than in the atmosphere. How do we typically address these? Well, a very common approach is to use hydrologic models that have some description of processes on the landscape and our watersheds, and feed those hydrologic models with climate inputs and climate predictions in order to reduce our uncertainty in the estimates of flood magnitudes, drought magnitudes, but not get rid of that uncertainty. So the uncertainty is there, and our goal really is to have an estimate rather than the correct estimate, because we're not going to get things right, but we do want to reduce our uncertainty. And that's the goal of any modeling application, but particularly so, in my opinion, in hydrologic impact assessment. So here's our modeling chain, kind of the big picture view. We take our emission scenarios, these socioeconomic guesses about what might happen in the future, take a finite number of those, which might be our RCPs, or now our shared socioeconomic pathways. We feed those emission scenarios through a general circulation model, and then downscale those to regional climate models, use those boundary conditions for regional climate models. We then realize that those regional climate models have errors. They have local errors that are not consistent with observed conditions on the ground. And so we perform bias correction to adjust those to compensate for the errors in the climate models. And then we feed those inputs into hydrologic models at variety of scales. And we're going to simplify things by just saying, oh, we only care to get stream flow out of these, although we might be asking for other diagnostics. Things are a little bit more complicated than that. In that, we typically need to deal with ensembles of regional climate models to deal with the great uncertainty, even for a single shared socioeconomic pathway. Our ensemble of climate models gives us a variety of possible inputs, and therefore a variety of possible responses from the hydrologic system. We perform that bias correction and downscaling, which I'll talk about a little bit. We then have to map those outputs to hydrologic units in our hydrology model. And there's some details to this that I think has been neglected in the past, that our group has been trying to address as part of that workflow. We then take a calibrated hydrology model, which has been trained from either historic meteorological data, raw data, interpolated met station data, or it has been fed by a reanalysis product, which is a combination of meteorological data and assimilated meteorological data in a regional climate model. So that's one instance of regional climate model that we use for our training of our hydrology models. And that's not necessarily, we're not actually calibrating it on a whole host of regional climate models. So those differences are going to play a part in our interpretation of results. We have a calibrated model informed by and trained by using forcing data that's been generated from a single regional climate model assembly with data assimilation. We then take that calibrated model, which we presumably trust, and we use that to generate long-term future simulations using the ensemble of climate model outputs. That's one way. Maybe it's a subset of that ensemble. Maybe we take the worst possible conditions because we're worried about the most concerning scenarios. Maybe we take all possible conditions because we want to know the uncertainty in those impacts. And then at the end, we have to, or would like to, be able to either perform bias correction on the hydrology model, knowing that it too has errors and we want to correct for those, or we perform uncertainty analysis on those hydrologic model outputs. So if we have some kind of uncertainty bounds that address the fact that not only do we have an uncertain climate future, but we also have uncertainties that are following through this whole modeling chain. There's errors in our model inputs, there's errors in our model structure, there's errors in our, or there's uncertainty in our scenarios, and all those manifest as uncertainty in our outputs. So with this chain, let's reverse a little bit and talk about what questions we ask of hydrologic models and what questions can we ask of these models. So given the current state of affairs, there's things that are easier for this modeling chain to address and things that are less easy to address. Things that we can realistically address with this modeling chain are things like shifts in freshet time. And we've consistently seen in the literature that we're going to see warmer climates are going to lead to earlier spring thaw, earlier melt. This is consistent. This is not as uncertain as things like the 100-year flood event. We can look at things like shifts in summer water availability. So average over longer timescales, shifts in summer soil moisture. We can look at loss of glacier source waters. We can look at water balance changes on annual scales. What's the change in average annual stream flow? What's the change in snowpack storage or the persistence of snow into the spring? Why can we look at these reliably? Well, I thought I animated things wrong. Actually, we'll go back here. So now let's look at the questions that are harder. The harder questions are things like shifting intensity, duration, frequency curves. These are used by engineers across the globe in order to design culverts and bridges and all sorts of structures. They are required for a lot of analysis by law in many cases. And these are shifting, and that's problematic. Engineers are like, oh no, what are we going to do? And we have changing magnitudes of low probability exceedance events. And these are magnitudes that we didn't really have a great handle on historically. And now we need to propagate that uncertain value into the future where we don't know those, where we really don't know those probabilities. And then we have changing things like probable maximum floods, which again, were really hard to figure out, even under the assumption of perfectly stationary climate. So what's the difference between questions we can easily or realistically address and the ones that we can't answer easily? All of these are often driven by the things that we're most confident about in our meteorological predictions, our long-term climate forecast predictions. Things get warmer, right? Nearly all of these are linked to things getting warmer, and we trust these predictions of things getting warmer. Climate models do better in predicting temperatures than they do in predicting precipitation. They do better in predicting the variability in temperature as compared to the variability in precipitation. So questions related to temperature changes, we're going to do better. These are relatively consistent between climate models. It's also reflected in the data. We can look at the last 20 years of data and we see that warming happening on the ground. You don't even need a climate model to do that. So we're going to be able to assess these reasonably well. The hard stuff is the stuff that is event-based, right? Climate models are not designed to predict what is the flow on January 15th of 2052. They're not necessarily even able to capture that variability in the extremes of precipitation. And which is one of the reasons why we have to perform bias correction. And our bias correction doesn't address all of the issues associated with event-based prediction over these long time periods. So these things, like shifting IDF curves, changing magnitudes, are not well captured by either individual climate models or ensemble climate models. And if I know we've got a lot of climate folks here and you'll challenge me on this, this is my personal opinion and I'm willing to be convinced otherwise. But this is my perception as a hydrologic model as I ingest these products. So this is difficult without climate models. And so it's going to be difficult with climate models. And our trends are highly uncertain. There's a lot of uncertainty associated with that. Unfortunately, one of the questions that engineers want to answer, have answers for, it's all of these guys. This is like, oh, it's going to melt 10 days earlier. Like, yes, biologists might care about that, but engineers are like, what's the magnitude of my 500-year flood event? And that's like, oh, geez, well, that's a really hard question. We'll get back to you. So, and all that uncertainty has another level of propagation down. So our extended modeling chain is our hydrology models are used to feed other models that require inputs of stream discharge. So those include hydraulic models. So if we want to make climate change impact studies of floodplain extents, we need to have flows upstream. If we want to know changing freeze up and breakup of ice formation and ice thickness on rivers, we need a hydrology model. Another level down. We want to assess stream temperature, ecosystem indicators that are linked to stream temperature. Dissolved oxygen and sediment transport in rivers. Reservoir operations and water licenses. We're going to need to propagate these hydrology models through yet another level of uncertain prediction. And then also we can have additional predecessors which bring their own uncertainty, things like forest fire models, land use models, etc. So that brings me back to what I do and what the Waterloo Hydrology Research Group does. We work on various components of these hydrologic modeling workflows, including some of the downstream effects, things like developing hydrofabric data products that are the basis upon which we build these models, so delineations of watersheds at the national scale. We work on calibration and regionalization strategies, machine learning and hydrology, hydrologic scaling, numerics, stream temperature, and water management. So this is myself, Professor Brian Tolson, and Professor John Quilty, and a team of postdocs and grad students all working on kind of this general area of problems. And I'm going to touch upon some of our research contributions as I move forward in the talk here. Many of our contributions are linked to this hydrologic modeling framework called Raven that was developed at the University of Waterloo. It's an open source tool for hydrologic simulation. It's multi-platform. It is not just a single conceptual model. It supports varying conceptual models where every modeling choice in a hydrologic model is subject to user intervention and customization. We can do things like represent structural ensembles, varying conceptual models of a watershed that allow us to assess structural uncertainty in addition to climate uncertainty. It supports things like stream temperature and synthetic tracer simulation and water resources management, which I'll talk about later in the talk. Raven has some unique features as we work with partners who are trying to do climate change analysis. It has some unique features that support climate change impact studies, including, first of all, it takes the outputs provided by and generated by climate models, gridded meteorological inputs in net CDF formats, and we can align our watersheds, which are not on a nice gridded geometry, to the gridded geometry of the climate models. So that is obviously very useful. Another thing, which I'm not aware of any other hydrologic model that does this, is that there are climate models that provide predictions that are using 360-day calendars or calendars without leap years. And it's a real headache to convert those climate forecasts. And I imagine some people in this room have dealt with this, as I hear laughter from the back. It's a real nightmare to try to convert this climate model data to the Gregorian calendar and provide predictions on certain days. Raven circumvents that by just being able to work with any calendar that the climate model does, handling time zone and unit shifts as well. Raven explicitly supports land cover and vegetation change simulation, which could be happening simultaneous with climate change. And so, and there's not a lot of models that can do that. And I'll show you some instances where we're actually doing climate change analysis that relies upon this land cover change. It's super highly optimized, so we can do things like run 100-year simulations that don't take 100 days computational time. We can run them in ensemble mode. We can perform climate calibration, uncertainty analysis in reasonable timeframes. And then, as I mentioned, we can use them to build model structural ensembles. So we can address more than just climate uncertainty, but all the other uncertainties that are in our predictions. Raven is not only academic, it's also the primary operational forecasting tool used across Canada by a number of organizational partners, provinces, and cities. It's also used by a number of consultants across Canada who have deployed hundreds of Raven models across North America, including for some high-profile projects like the $16 billion Site C dam on the Peace River and the $8 billion Trans Mountain Pipeline assessment for hydrologic impacts. And it's also regularly used by consultants for climate change impact analysis. Raven has some ties with Oranos that we've been working on over the last few years. Raven is the hydrologic model that underlies the PAVX hydro system, which is a Oranos product, which provides hydrologic modeling as a service that it really is intended to streamline the process of doing climate change analysis on watersheds across Canada. Raven's also been a part of some other projects, including the recent InfoCrew project with some folks from University of Laval. That should be a capital L. Sorry about that. And we're also currently part of an Oranos-funded temperature simulation project with UQO. Okay, so now I'm going to get to some challenges. I'm going to get some background here, and I'd like to go through, and we'll start with an easy one, which is data access, which the folks at Oranos have made a lot easier. So thank you for that. We often have the issue where GCM and RCM results are issued as massive files covering the entirety of North America or the entire globe. And we want to use them to represent a small drainage area in Southern Ontario. And so we have to download this giant mega file or mega files, stitch them all together, cut out our area of interest, convert it into something usable by the model. And so each and every consulting agency in North America has reinvented the wheel doing this. Every university research group has their own workflow for doing this. We have used, after doing it ourselves for so long and hating doing it, we now rely on PAVX to do the work for us. And we recently applied this into some work for the IJC in the Milk St. Mary along the Alberta-Saskatchewan border. And so this PAVX hydro system has been really useful for us. This was developed, the PAVX hydro project was developed mostly by Oranos, the ETS, with some moderate support from Waterloo, but it allows for calibrated models to be deployed on 5,700 basins across North America, using various model configurations and a whole bunch of different bias-corrected regional climate forces, run on the Oranos servers. So this is probably known information to most of the people in this room, but for people online, this is worth looking into. It's a valuable service. The other challenge we run into is that climate models aren't right. They're not perfect predictors. And so we know that they have biases in estimation of meteorological variables, and this is due to a variety of reasons. There's unresolved or unknown physics, incomplete knowledge of both physics and how clouds form and all these other things at the resolutions that these models are run at. And if we look at the biases, so this is a little bit outdated. This is CMIP5, which is what I could find easily as I was building this talk. So biases in the annual temperature, this is a bunch of different climate models on the bottom axis. And this is, I think, spatial variability on the y-axis. And so we see the variance in the bias at the global scale, annual temperatures. So, and also with precipitation. And for precipitation, if we look at this, this is this is annual bias. Some of these climate models have precipitation biases or had precipitation biases of as much as 100, 150% for annual precipitation. So that's not event precipitation, that's annual precipitation. So if we look here at the spatial multi-model mean precipitation bias, so this is the mean over models, this is the mean over time. So we're taking the mean of an error over time and over models, and we still can get, in Canada, roughly like a 0.75 millimeter per day bias, which manifests as an annual error of 275 millimeters per day, which is as much as 30% of the water budget of many of the places in Canada. And that's for an annual average. And then we want to be able to make predictions about events. And so this is a big deal. This is a problem. And so this is basically a requirement for any hydrologic model application, is to compensate for those known errors. So how do we do that? We develop an empirical CDF of observed values. This could be temperature or precipitation. And we take the climate model and we run it in the past during the same period. We generate an empirical simulated distribution, cumulative empirical distribution of those same variables. And then we induce a shift into the future. This is one way of doing it. There's many ways of doing it. This shift could be spatially variable. This shift could be applied uniformly across the domain. It could be applied at certain points. There's all sorts of tricks and stuff in the literature, but this is generally what's being done. But the key here is, because this is an empirical CDF, we might be running the model only 50 years, 75 years in the past, where we have iffy data as we go further and further in the past. And we're doing a bias shift at the extremes of this empirical CDF that is itself uncertain. And so this bias correction is dramatically adjusting often the extremes of our distribution, which is, again, as hydrologists, that's the stuff we're interested in. So we have real issues in interpreting low probability events, these extremes. There's less information informing bias correction, because we might only have one or two events with a probability, with a low exceedance probability. And it also requires more dramatic adjustments between our model, our climate model, and our data. And then the other big assumption is that we're going to assume that this bias is the same in the future as it was in the past. And that's another definitely invalid assumption, but we can't make any better assumption. We have no way of knowing how that bias is going to propagate in the future, forward in time. So we then take these bias corrected results and downscale them. I have no concerns about the downscaling from GCM to RCM, maybe just because I don't know enough about it. But that's just feeding boundary conditions to a locally higher resolved model. Good, that works. What is a bit harder to deal with is some uncertainty induced from statistical downscaling, which is taking the results from regional climate models and downscaling them to a finer resolution using empirical relationships that between spatial variables that allow us to adjust temperature and precipitation, often to handle things like orographic effects, elevation effects. And this is really a form of artificial precision because it wasn't in the original climate model. And if your watershed is this big, tiny little watershed, that downscaling choice really has a strong impact on the results of your hydrologic model. So we have bias issues. Let's see how I'm doing on time here. Terribly, doing terribly on time, but I'll catch up. All right, so we have bias correction and downscaling are fine for generally respecting statistical characteristics of data. So figuring out things like mean winter temperature, that's fine. The problem is, what we care about in our hydrology models is we want it to specifically respect the data. We want it to get the probability distribution of precipitation, especially those low exceedance magnitudes, right? Does our bias corrected model capture things like the 100-year, 3-day precipitation magnitude? That's what we need. And that's not something that climate models can easily give us. And so there's uncertainty associated with it. And then we have the persistence of that bias into the future, which is unlikely. And so in the long term, what we as hydrologic modelers want the climate modelers to do is, we don't want you to bias correct your models. We want better models, but we probably can't wait for it. right? So in the long term, we want bias reduction. It's better than bias correction. Well, we'll deal. Other things we have to deal with is event persistence. So it's known that climate models have issues with under or overestimating consecutive wet or dry days. So our bias correction only is correct if we have daily bias correction, where we're using the daily data and correcting it daily, using the daily statistics. We're missing out on the 3-day statistics and the 7-day statistics and the 30-day statistics that might be important for, let's say, drought analysis. So our bias correction corrects distributional stats at a specific time interval, not all time intervals. So it doesn't handle things like autocorrelation of consecutive precipitation events in consecutive days. Another issue is that we have a lot of climate models generate coarse resolution outputs, and a lot of hydrology questions require hourly or finer inputs. So this is an example of a hydrograph in a small urban basin. The difference between the hourly and the daily average results are significant. And we can't just aggregate this and assume to get results that are going to be useful. Here's one that we've kind of stumbled upon in our work at Waterloo that we weren't really thinking about prior to, but it's very common for hydrologists to take the results of the bottom layer of our climate model and take air temperature. Okay, that's our air temperature for this HRU here. The problem is our climate models don't conform to the actual topography of the landscape. They're often smeared out in space. Why? Because that smooth model grid makes the model stable. That smooth model grid means that the centroid of this cell that reports a temperature is not the same as the mean surface elevation of the actual topography, which is not the same as the surface area of our computational unit in our hydrology model, which means we have to correct for the presence of this smoothing by mapping to the correct elevation from our geopotential heights, which are embedded into the climate model. But this step is rarely taken by hydrologists, and we found that it matters. All right. We also have the calibrate. So challenge. I've got lots of challenges here. So 5, we're down, 4 down, 4 more to go. Calibration to simulation disconnect. We calibrate hydrologic models typically to stream flow data informed by forcing inputs that are either infilled met data or reanalysis products using a single climate weather model realization informed by interpolated data. So things like the Canadian precipitation analysis data set. We then run under future climate conditions using bias corrected model ensembles that don't have the same characteristics as the training data, and they're not going to have the same characteristics as the training data. So we're going to have, when we calibrate the models, we're compensating for issues potentially that are present in kappa that are not going to be, and the other climate models are going to have different issues. And that compensation is going to manifest as more uncertainty in our outputs. So another issue. Scenario selection, I'm going to bypass that one, although that is a concern. We use all of our climate model outputs. Do we select a subset of them? Do we cherry pick the worst ones, which is very common in the literature? Just take the worst and say, oh, we'll prepare for the worst. And then I'm going to get to a key challenge, and this is most of the problems that we face at the University of Waterloo, is trying to solve hydrologic modeling problems in general, not necessarily specific to climate analysis, is that even if we had perfect meteorological inputs, which we never have in the past or in the future, stationary conditions, there's still a lot of modeling challenges we have to address. So one of the things that we've addressed at Waterloo is handling the influence of lakes. And this is surprisingly has not really been regarded very much in hydrologic modeling, but it's super important. So this is, we worked with Environment Canada, gem surf forcings on a model of the entire Hudson Bay watershed where we had runoff provided by that Environment Canada land surface scheme. And we ran it through a system, their system, which represented only the large lakes, and our system, which represented 15,000 lakes and 26,000 subbasins. And with no calibration at all, we see a marked improvement in performance just by including those hydrologically important yet often ignored lakes in a place, the Hudson Bay watershed, which is just covered in lakes, right? This is pure Canadian shield, thousands of lakes. They have an influence. Even without calibrating them, we see the benefit of addressing that influence. And as a byproduct of this, our team, led primarily by Brian here, has worked on the development of what's called a Canadian Lake and River Hydro Fabric. This is a nationwide routing product where, so this is an example of it for the Lake Nipigon, north of Thunder Bay, where we discretize the entire landscape into rivers and lakes and their local contributing areas. So if we zoom in here, we can see that we break things up into local contributing areas of individual lakes and the connectivity between all of our surface water features across Canada. And we've done so in such a way, using some tricks developed by the Ontario MNRF and used by Environment Canada, using some tricks such that this blue line network in our delineation nearly 100% respects the NHN, which is the National Hydrometric Data Set, their polyline delineation of all the rivers and lakes across Canada. So when you do this, traditionally use terrain analysis, which has all sorts of issues associated with the DEM. We can avoid those and get very, very high quality approximations of our catchment areas, again, across Canada. This can be used for more than just modeling. So we're trying to let people, as many people know about this as possible. And we encourage you to visit the CLRH website to take a peek. All right, so some more problems, challenges in hydrology. And again, where's the clock? I lost it. All right. We're still having trouble building models that adequately describe historical conditions. Just like climate models, we have the hardest time with predicting extreme conditions. Unlike forecasting applications with scenario analysis, we can't lean on data assimilation to do the hard work for us. So a key thing, and this is something that, again, we focus on quite a bit at Waterloo, is ensuring that uncertainty in the and due to the unknown hydrologic model skill in the future has to be cooked into any climate change analysis. The very least, we look at errors in our estimates of floods in the past, and we propagate them forward in the simplest fashion. So we know that we get floods right within plus or minus 20% of the magnitudes. And we say, we're going to expect that our future predictions are going to be wrong by plus or minus 20%. That's the laziest version, but it's better than not doing it at all. Better than that, there's techniques in approximate Bayesian computation and some post-processing model uncertainty techniques, which we're developing skill sets for in-house that allow us to estimate the error in the model and propagate that forward in the future. And I don't have time to get into any of that. Another interesting thing is challenges due to hydrologic response change. So the landscape, not everything is directly driven by meteorology. It's not like if we just had a perfect climate forecast and ran it through a very good hydrologic model, that's one from the past, that it would give us a good prediction of the future. Why? Because the landscape itself is transforming due to impacts of climate change. And so we need to have the mechanisms to be able to represent those feedbacks in our hydrology models. So things like permafrost melt leading to landscape change, shrinking glacier extent, or shifting reservoir management. So here's an example using Raven. This is some work done by a consulting agency out west, Mac Hydro. This is melting glaciers in the Athabasca River Basin. And an interesting thing about melting glaciers is as they melt, their footprint changes. And so we have to represent that changing land cover as the glacier declines. Otherwise, if we use a single stationary glacial extent, we dramatically overestimate the melt being generated from that glacier. And so they use that land use change feature in Raven to propagate the footprint of the glacier footprint, in addition to some of the tracer functionality in Raven to be able to figure out how the hydrograph shifts, but also how the component of that hydrograph, which is generated from glacial melt, shifts over time. So this is our historical conditions. And then we have future conditions under 2 RCPs, and we see a significant diminishment in glacier outflow mass. And this is going to cause reductions in available water in when we need it most, in August, September. Well, this should not, I don't know why that's not there. Yeah, this slide just didn't take the figures, so I'll have to talk about it, which is much harder because that was a useful figure. Okay, so this is some work up in Scotty Creek in the Northwest Territories. The team at Wilfrid Laurier University has done a lot of field work up there, and what they found is this is discontinuous permafrost terrain. So we have spotty permafrost where there is no permafrost beneath our water storage features, fens and bogs, and there is permafrost in between those underneath what's basically the stable land surface beneath raised peak plateaus. So it's frozen beneath raised peak plateaus, but not very deep. It's on the order of 1 to 3 meters of permafrost. We have things like the active layer not freezing through all the way to the permafrost, so we get a liquid water region in between frozen soil and permafrost beneath. Water is conveyed during the winter that wasn't historically. And we have frozen regions that have started to thaw, and this actually changed connectivity because as you have things like a bog and you thaw out the downstream end of that bog, it then can release water because we basically have like a weir that it allows to overflow down to other features, which I had great graphics for. You guys would have loved it. And so what we did was we developed models of the Scotty Creek Basin where we tried to make predictions using machine learning of what the landscape will look like 90 years from now, propagated these through models, and we see that interesting that what we don't see elsewhere is we actually get changing runoff ratios over time as the permafrost thaws melts. The interesting thing is this is the observation we've already in the last 20 years, this is actually the worst case scenario has already happened. In the last 20 years, we see rapid melt, and then we end up plateauing because we're running out of things to melt. And so this, but our future projections show a consistent increase in runoff ratio, more water reaching the stream outlet, less water stored as those bogs no longer have edges to the bowls holding the water in. They're now melting away. Some future work. Again, keep my eye on the clock. Newest version of Raven, which just came out this January. We have we now can support very sophisticated water management representation. So it's treated as an optimal solution to manage systems with competing and conflicting management goals. So we can have things like irrigation demands, maximizing hydropower earnings, satisfying environmental flow restrictions, target stages for flood management, all in a single watershed model. So you can do things like assess like watershed-wide planning and strategies for mitigating the impact of climate change. So oftentimes things like reducing drought impacts in agricultural areas where water availability is an issue. And so Raven is unique in that it is a coupled hydrology model and water management model. And to my knowledge, it's the only one that really does that. Now, we haven't really deployed this for climate change yet, but once you have a climate coupled water management hydrology model, we can do things like explicitly test resiliency of management strategies and policy implementations to uncertain future climates. Because you can codify those policies as management goals, and then you can adjust those goals and the statement of those goals and test them within a climate change scenario analysis framework and go, under what conditions does this goal fail? Can we adjust it so that we, over multiple realizations of climate models, climate scenarios, do we mitigate and minimize the damage from climate change by making good management choices? And I think this kind of approach is going to be way preferable to preparing for things like frequency-based and therefore almost impossible to know scenarios of concern. We're better able to react for any possible scenario that could be thrown at us rather than and trying to prepare for that than saying, let's prepare for the 100-year storm event and that we don't know, and that's it. So actually, maybe I did tighten things up in time. All right, so now I'll talk briefly about interpreting uncertain impact predictions. So depending upon our hydrologic item of concern, the thing that we're trying to determine impacts associated with it, we're going to have different sources of uncertainty. For simpler impacts, most of our uncertainty is going to be due to that uncertainty in climate prediction. And if we use all of our climate models and feed them through our model, because that's our primary source of uncertainty, that's going to capture most of our variability. So this is some work done by Jean-Luc Martel and the group at ETS, where they looked at a variety of different hydrologic models, run with a range of different GCMs, and looked at the variability in things like mean annual stream flow. This is one of those things that I said is an easier thing to predict. The variability between models is very small, which means that the uncertainty associated with the model choices and parameterization and calibration and all that other stuff was small relative to the variability associated with the climate model, which is the range of the whisker plots here. And this is useful because this tells us for these simpler problems, we don't have to get all fancy with our hydrologic model uncertainty analysis. We can just propagate through all our GCMs or all our RCM results and be confident that we at least have characterized our range reasonably well. This will not work for more sophisticated problems. If we want to figure out the change in the 100-year event, there's a whole bunch of additional sources of uncertainty. We have how well does our model predict the 100-year flow or the response to a 100-year flow? Does it get the flood within 5%? Or does it get it within 20% or within 50%? That's a massive source of uncertainty. And we can be off by 50% if we don't have a well-designed model. We also have the uncertainty associated with estimated 100-year flows from a finite data record, right? So there's already uncertainty associated with the frequency-based methods, things like plotting point uncertainty that are very large. If we have 50 years of record, how do we estimate the 100-year precip event? You can do it. We can fit some probability distributions in it through it, but there's still a tremendous uncertainty in that estimate of what it is. Again, even without any climate change. But this is a big source of uncertainty when we try to look at probabilistic impacts, probabilistic risk. And we also have the climate uncertainty. So all three of those things now pile up on top of each other and make it very hard to answer some types of questions. I can't say I'm like super intimately familiar with all the literature out there because it just keeps coming in a flood. But I haven't seen any really good solutions to this latter issue. So Waterloo Group here is working actively towards model-based uncertainty analysis for low frequency events without climate change. And maybe someday we'll get to the part with climate change where things get harder. You guys have no shortage of problems faced in this room to figure out some of these really hard questions. All right, so the take home here, climate change simulations are really becoming a big part of what hydrologic modelers do. It's becoming our bread and butter. Unfortunately, both the bread and the butter are highly uncertain. So there's a tremendous amount of uncertainty in all of these analyses. So some best practice, again, use the best available downscale climate predictions. You want to understand that there are some reasonable questions, important questions that we're not going to be able to answer or not going to be able to answer reasonably, easily, and we may not get answers at all. The process of chasing after those answers, though, and getting something even with a wide uncertainty bound is more valuable than not having any answer to the question. We should always be using model and scenario ensembles because there's too much uncertainty to disregard. And an important thing, this really for the consultants out there, that it's important to work with the median of the impacts from the individual models rather than the impacts from the median model. We can't just take the average of all of our climate models, feed it into our hydrologic model, and expect that the impacts are going to be our somehow best approximation of our expected impacts. We have to do it the other way around. We have to run many models and then look at the distribution of possible impacts. If you want to go with the mean of that at the end, that's fine, but that mean is not going to be the same as what you get from doing it the lazy way. And then really the best thing we can do is design for resiliency rather than unknown and unknowable low exceedance probability event magnitudes, which we're just in many cases not going to be able to get our hands on. And I'll take questions there. By the way, this is from our colleague at Ontario MNRF, who's an amazing photographer. So he took this shot.
Well, James, kind of object to your use of probability here.
Okay.
In a sense, that I think that, well, probability means it's a description of what you know,
Yes.
right? And if you don't know much, the probability distribution is going to be very flat. If you know things well, it's going to be peaked.
Yes.
But he seemed to use the term as in a frequency of occurrence rather than a
So
probability.
many of our specifications are described as a frequentist approach, right? So those probabilities, so yeah, we have to think, I probably use terms probability and likelihood as being interchangeable. But what I'm talking about is we're trying to assess things that can only be described probabilistically, right? The 100-year flow is a statistical definition. It's a frequentist definition that if we have an infinite number of years of data, we can describe perfectly. The uncertainty is in that probability estimate because we don't have 100,000 years of data or correct model output in order to infer that value. Is that a?
I'm going to argue with you.
All right, we can argue about that at lunch.
Both questions.
To go back to one of the issues that you raised, I think it was number 4, when you were talking about the level of the model.
Yes.
So you see, you take the lowest, the value from the lowest model level, is that?
Yeah, so the common practice is to take the surface temperature.
Which is
This guy here,
2 meters.
we take the surface temperature at 2 meters.
Yeah,
But that 2 meters is described on a smoothed out climate grid.
Yeah.
Right? So it's 2 meters from the bottom of the climate grid because it's assuming that the topography is actually this surface, which is the bottom of the climate grid, which is not the same as the actual physical surface. And because we perform that smoothing, there's topographic effects that get neglected in the climate model that are actually present in the real world.
because basically, because the topography of the model doesn't match the observed topography, so there's a discrepancy between the two that creates a problem.
That's right. So it might be assuming, and we have to dig in and get the geopotential height from the climate model that corresponds to the elevation actually used in the climate model, roughly, and then perform a mapping back to our computational unit that does the corrections for that.
And then what will be the impact of not doing that exactly?
So for instance, if your temperature, if the climate model is overestimating its elevation, it's gonna assume a colder temperature than is actually present at that location. And these differences are not small, so they can be 200 meters off in BC. And 200 meters is the difference of having a meter of snow on the ground and having no snow on the ground in some cases.
Which is especially important to the Rockies.
Yeah, so this is Ontario, this doesn't matter at all. In BC, Alberta, this has definitely shown to be important. Like there's an influence there because of everything depends on what's the percentage of snow covered area at any given point in the year. Like that, those orographic effects are super important.
Exactly.
I have a vague conceptual question because at the end you mentioned that it's better to give an answer with like huge uncertainty bar than no answer at all for like these engineers that are, you know, that need a number in their model. But you have like a kind of mental model of like what is an answer that's you can give to an engineer versus something that you would not. Like where's the kind of garbage?
Oh, what's the cutoff on yeah, no. So yeah, sometimes when you're dealing with all of these uncertainties, like your uncertainty bounds are so massive, it's very hard to say, what do we do with this? And I actually don't really have a good answer for that other than our job is to characterize how wrong we might be. And if you don't try to characterize how wrong you might be, you're not hedging your bets for the possible futures that you might, and as an engineer, that's super important. Like we're very conservative as a breed right? We don't want to say we're gonna design it this way, according to this median value, and then find out that we're wrong 2 years later because of a failure. So it's better, again, to do something to characterize that uncertainty. I don't think there's a threshold when it's too much uncertainty or too little. It's a judgment call what to do with that. But by not trying to ascertain how wrong we are, we're gonna get ourselves in trouble.
We'll try to go online for a few questions. So Cody, you want to unmute and speak up, please?
Yes, hello. Thank you very much for your presentation. That was really great. I have a question about the recommendation for designing for resiliency, which I think I align with that. And I'm just wondering whether you know or have a recommendation or insights regarding which modeling framework would be best suited for designing or managing for resiliency and water resource management, and if the Raven model allows for the evaluation of different resiliency metrics within it, or where you see that going in the future.
So you're gonna get a very biased answer from me as the developer of the Raven model and the water management model.
Yeah.
This kind of analysis can be done with any good water management model. However, there are benefits to having a couple, especially with climate change analysis, to having a coupled hydrology water resources management model, because you're not having to chain these all together, run multiple hydrology models through multiple water management models, but also there's feedbacks there. There are feedbacks where management decisions can change landscape hydrology, for the instance of return flows, where we change our availability of water, that changes how much irrigation is put on the land, which determines how much irrigation return flows back into the stream, which is based upon soil moisture, which is a high hydrologic model predictor variable. Most management models don't have that. The other problem, and this is probably the more salient one from an engineering standpoint, is the capable water management models go for about $13,000 a pop per site license per person. They're all proprietary. Raven is open source, and it does most of what the good ones do. And so, again, from a consulting standpoint, I think that's a very good argument to be made. And one of the reasons why we put this in here is because there's a need out there for open source management models that can solve real problems. And there's not a lot of those out there. But in terms of being able to calculate all those resiliency metrics, all of that is easily evaluated from the outputs from Raven.
Thank you very much.
So again, very biased answer, but I don't know if I'm capable of giving you another one. So.
Thank you.
Yeah.
Thank you for the presentation. It's a really good presentation. I have a question about the mod. You have many emulated modeling Raven. Which one is the most popular within your user and why? And second question is, do you have a model that takes into account not only the water but also the energy budget?
Yeah. Actually, I thought I said a slide in there. I just skipped over it completely, didn't I? Oh, yeah, I neglected to include my stream. So Raven also supports stream temperature simulation. So it does a full thermal energy budget, mostly again for stream temperature, not for, well, it does land surface fluxes. I'd say it won't do it as capably as a land surface scheme, but for getting stream temperature and lake temperatures and incidents of freezing, that kind of thing, it supports that. Now that's a lot harder to model than water flow because it's a lot more sensitive to local variations in stream flow, channel characteristics, incoming radiation, shading, and all those other things. There was another part of your question. Oh, popular model. So most popular implementation in practice is probably HBV. So the HBV variant. Although everyone builds their own version of everything, and the thing about Raven is you start with one of these templates and you adjust as necessary. So at this point, I'd say that everyone has their own version of a handful of these models, like HBV and UBC watershed model, that are not quite the original. And that's intentional because they're taking a model that is tried and true and has been demonstrated in many locations, and they're revising it for specific locations. They're saying, well, in Southern Ontario, we have tile drains, which are not respected in any of these models. We have lots of depression storage, which are not respected in any of these models, and so we need to add those things. So while I say that's the most popular like base model, there's a multitude of variants out there that are used with good effect.
Although there are questions remaining, I'll close the session online, and thank you, James, again for your great talk and answers to questions. Thanks.
Thanks.